Okay, what about Q3? Yeah, question.
How do you know that it was supposed to be the falling edge?
Because of the circle there. I should have pointed that out to you. But if you chose them all to be the same, all rising edges, all falling edges, it would still work out.
Because mine ended up starting at 111, then it went down.
Yeah, a little strange. But if you go with all falling edges, it works out nice. Okay. So this guy here can do what now? It's at 0, but it can't change its state until what? Okay. So look what we've got going on here. Let's count this guy right here. One thing, yeah, let's count. So we'll come over here. Okay. 0, 1. What's this? 2. What's this? 3. What's this? 4. You understand what's going on? All right, look at this now here. 0, 0, 0, 0. Look at this. 1, 0, 0, 0. Look at this. 0, 1, 0, 0. You understand that if you start counting, start counting. 0, 0, 0, 1. Next one is 0, 0, 1, 0, 0, 0, 1, 1. Okay. Do you understand how this thing is a counter? It's like a 4-bit counter. So you could count how many things? 16 things. There's 4 bits here, so we can count 16 things. What would we do if we wanted to count 10 bits? Add more of these flip-flops together. Is that all right with everyone? Okay. So this is a number system here, if you will, and next period we're going to start on numbers. We're going to start on positive integers, negative integers, and then the following time on Friday we'll start talking about floating point numbers and how we represent them. Everybody doing okay with this? Okay. So with these flip-flops, we can make registers. We can make shift registers where things shift down. Okay, so if you wanted to make a shift register, a serial shift register, you could take these and just go into the outputs to the next. Now what's going to happen, if they're all clocked the same, whatever gets here gets popped into the next one, then to the next one, to the next one, so this would be a shift register. So this would be a serial load. So I've got a 3-bit shift register shown there, but I could certainly make a 10 or a 20 or however many bits I need, and then serially shift in the information that I want. There are also ways to just dump everything in one fell swoop, so that there are some of these that we can preload them in parallel. So we give it a command and we say, bam, we're going to make your Q do what we want it to do, either a 0 or 1, and we can do all of them in one fell swoop. So that would be a parallel load. Okay, now with the shift registers I've shown you and with various inputs for the J and the K, there's not enough inputs to do a parallel load. So just realize that we can serially or parallel load these things. Everybody okay so far? All right. Okay, so we want to talk about memory now. These are shift registers. We're going to find out that our microcontroller is going to have bunches of these shift registers in there that we can do stuff with. Well, yeah, I'll pick up from there another time. So let's talk about our memory. So we talked about cross-couple gates. Okay, so this was what type of a flip-flop? Almost. Set bar, reset bar, flip-flop. So that in order to have it be kind of in a static situation, we'll have both the set bar and the reset bar lines high. In other words, a bar means that that variable is active. So we can store information here, and it will stay there for as long as we want, almost. There is another way that we can make a memory cell, and that's to make a, so let me put a fuse in here. So I've got a fuse. Everybody know what a fuse is? Yes, no? Anybody not know the term fuse? Okay, so what's a fuse do?
It limits the amount of current that can go through an object.
Okay, and it limits it how?
I turn it into an open circuit if it...
Okay, it turns into an open circuit. Some of them are resettable, others, once you blow them, they're gone. Okay, so in your house, the circuit breaker, resettable fuse or non-resettable fuse?
Resettable.
Resettable. If you've been to maybe your grandmother's house, they used to have these little things that look like a light bulb that screw in. Once those go, you replace them. Okay? But a fuse is to limit. All right. So in this state here, if this is a memory cell, what variable is at the output? Now wait a minute. That's a fairly large resistor. What would you expect the on resistance of a fuse to be? Pretty low. So let's take something low. Let's go with 400 ohms, and we'll make this 100 kilo ohms. Okay. So what voltage approximately do I have out? Heavy sigh. Approximately 0, right? I mean, we've analyzed this 400 times already. Right? Approximately 0. What happens if you blow the fuse? So at the factory, you say, oh, I'm going to blow that fuse. Now what voltage do I have out? Or what logic level? 1. Is that okay? So at the factory, you could have a gazillion of these guys, and you could, now, how you read the information, we haven't talked about. But here's a cell that we could store information into. Okay. So what happens if you write a 1 there? Are you ever going to be able to write a 0? The answer is no. There's no little switch in there that you can toggle it back. Okay. All right, so now let me take, and I'm going to do exactly the same thing here.
Dr. Ryan?
Yeah.
What does it say at the top of 100 kilo ohms?
This guy, VDD.
Okay.
Yeah, that's our 5 volts. Okay, so we got a large resistor there. Now, that bottom device looks like what? Pardon? Looks like a NMOS device, yes? You notice I got a little extra piece of aluminum sandwiched in the glass? Interesting. Okay. If I put a very, very large voltage, now I'm not talking thousands of volts, but 20 volts, something like that, I can kind of I can put a little bit of charge in there. And once I get that charge in there, is there any place that it can go? I'm not telling you I magically put it in there. I apply enough voltage that I get it in there. I don't break anything, but I get some charge in there. Once that's in there, is there any place for it to go? The answer is no. Because it's what? It's sandwiched between or in glass. So if that has positive charge on there, is this guy on or off? Okay, let's, no, wait a minute. Okay, I'm just going to forget that for the time being. I'm going to put 5 volts here, that device, the MOSFET on or off? What's its gate voltage? What's its source voltage?
0.
Gate to source voltage?
5.
On or off? Say it again. On. Okay. So what voltage do I have out here? 0 again. Correct. Okay. And if I have 0 volts here, then the device is off and I have logic level 1 out there. Well, now what I'm going to do is I'm going to put that little chunk of aluminum in there, surrounded by glass, and I'm not telling you how, but in some fashion, I'm going to put positive charges on there. Now, I don't care whether I've got 5 volts here or 0 volts here. What is this device, what's its state going to be?
On.
On. This guy will be on, and therefore I'll have 0 volts out there. What happens if I bleed all that charge off there?
It's off.
It's off. Ah. Okay. You understand what's going on? Okay, how long will that charge stay on there? About 100 years.
So are you saying like it doesn't matter what voltage you put in if the piece of aluminum is charging the rest of it?
Well, I'm going to put a large voltage on here to drive some charges onto that little chunk of aluminum in there. Okay. And then it's going to stay there, and it can't go anyplace. And so now it doesn't matter what I have here. This can be just floating out there, and that gate's still going to be on. Okay. Okay. So do you see that I've made another memory storage device, right? If I put charge on there, the device, what value do I have out? 0. If I don't have any charge, what's coming out? Now, resistors are very difficult to make. They take up a lot of real estate. You'd probably use another transistor up there. Is that all right? PMOS device or something. But you understand the concept here. Okay. Now, there's another way that I could do this. What did we say this was here? Glass. Here's a conductor. Here's a conductor. 2 conductors separated by a dielectric. You've made what? Capacitance. So what happens if I put 5 volts on this guy here? What's coming out? Please say 0. 0? Now, I'm going to take that away. No more 5 volts. Is the device on or off?
Immediately it's still on.
Why is it still on?
Because it needs to
He charged
decharge.
the capacitor up, right? But you leave it there, and you leave it there, and you leave it there, what's that charge going to do?
Dissipate.
It's going to discharge, all right?
So the aluminum will last like an infinite amount of time, where the glass will be like a small amount of time.
Well, remember, this is a capacitor here. This is the same thing here. I'm trapping a charge inside the dielectric material. Okay? Everybody doing all right? Okay, so I have showed you several ways that I can make a memory cell. Yes? All right. So now, we want to start defining some terms here. RAM. Heard the term before?
Mm-hmm.
What does it stand for?
Random access memory.
Excellent. Random access memory. What it means is that you can get at any location in memory just as fast as you can get to any other location. So in your computer, is your RAM memory, can you get to any part of it just as fast as you can get to any other? The answer is yes. Now think of what would happen if you had all your data stored on magnetic tape. Does everybody understand the term magnetic tape? Thin strip of tape that's got magnetic material on it, and you roll it on a reel. Okay? So you got this reel full of stuff, zeros and ones stored in the polarization, or the how you polarize little domains of chunks on that medium. Can you get to any memory as fast as other? No. What happens if it's in the bottom part of the spool? You got to unwind it, right? So that would not be random access. Okay. Now, random access is slightly a bit of a misnomer. Yes, it's random access. We're going to find out other memories random access as well. But random access really means read and write memory. So I can both read and write to this memory. Is that all right? So some of these terms for a given chunk of memory, several of them are going to apply or not apply. So, okay, what do you suppose that ROM is going to stand for? Read only memory. Do you suppose that your ROM is random access? And the answer is yes. So you've heard of the BIOS chip that you've got in your computer, that when you fire it up, that's where it goes and starts the whole process. Okay. So that's read-only memory, but it's random access. Why do you suppose you would want to have read-only memory? Yeah, so it can't be changed. So nobody can go in there and diddle with it. Is that all right? Okay. We could talk about PROM. The P stands for programmable. Okay, which ROM is generally made, the standard type of ROM is generally made at the factory. So of my types of memory that I showed you over there, we started with cross-coupled gates, and then we went with fuses and all it and everything else. Which do you suppose would be the ROM type of memory?